Hi, this lecture is an introduction to some of the physics involved in the quantum harmonic oscillator. What I'm going to do is I'm first going to review the classical problem, and then I'm going to show you what it looks like to do the quantum mechanics problem. So the reason people study the harmonic oscillator is because it is a realistic localizing potential. That is, it's applicable whenever you want to model a particle being sort of stuck somewhere where you want something more realistic than something like the infinite potential well, which has an unrealistic, infinite force only at the boundaries. In this case, we're going to have a smoother force, which is more like what you might see in normal old realistic nature. So it's often the first approximation for localizing a particle in a realistic physical situation. That's why people study it. So the classical problem really is, it's a mass attached to a spring where the mass is of mass m and the spring has constant k, and it's necessarily a Hooke's law spring. And that's the classical problem. It's not a more realistic spring, which doesn't necessarily follow Hooke's law. Hooke's law, if you recall, is there's going to be a force on the mass m, which is always the opposite direction to how much the mass m has displaced by. And so the idea is if the mass m is over on the right-hand side of an equilibrium, we'll say that this is a positive value of displacement from the equilibrium, and this particle is experiencing a restoring force. So the minus sign is for restoring or localizing. It's a localizing force. And you can define a potential energy. It'll be 1/2 kx squared. And the reason that this is important is because if we want to quantize the harmonic oscillator, we're going to have to put a potential energy function into Schrodinger's equation. So that's why we need to keep track of it. So the classical answer has, for how this particle is going to behave, is the energy of the oscillatory system is going to be 1/2 mv squared, right? That's the kinetic energy of our little particle, plus the potential energy, so 1/2 kx squared, right? And this will be the total energy. And if you use the conservation of energy, then in this potential, it's just like you imagine a little ball just rolling back and forth in this confining, localizing potential. And it's going to have an overall frequency to the motion, right? Which is 1 divided by the period. So the period is the amount of time it takes the ball to travel from its high point on the right over to its high point on the left, but then back, right? The period describes how long you have to wait for your system to look exactly the same again. So the ball needs to be on the same side when you check again. And that frequency is actually related to the mass and the spring constant. And it is 1/2 pi times the square root of k over m. A nice thing to describe instead of the frequency is this thing called the angular frequency. So this angular frequency is the result of multiplying f by 2 pi, so it's the square root of k over m. All right, so the first step that a book typically takes with quantization of the harmonic oscillator is instead of imagining there's actually this classical spring, right? Classical spring in this quantum problem doesn't make any sense actually. So instead of imagining the classical spring, they imagine that there is some sort of interaction that's going to give rise to this oscillatory localization of the particle. And the oscillations are described by omega. So in the quantum harmonic oscillator, the idea is there is no such thing as a macroscopic spring doing our harmonic oscillation. There's some sort of microscopic, nanoscopic interaction going on that's giving rise to some reason for our particle to be localized or confined. So it's more natural to go and directly talk about the frequency of oscillation, which is right here and related to the spring constant right here. So what we'll do is we're going to solve for k, right? Solve for k. So square both sides. Omega squared equals k over m. So k is equal to m omega squared. And so instead of a classical spring, we're going to imagine that there's an interaction that is somehow described by this thing right here, which is m omega squared. So we'll say that there is an appropriate potential energy for our super small, little tiny nanoscopic situation, quantum mechanical situation. And instead of writing the potential energy as 1/2 kx squared, we're going to replace k with m omega squared. So it'll be 1/2. All right. An interesting thing to do is to remember that the conservation of energy only allows the particle to get out to a maximum position x away from the center. Because when that particle gets to that maximum sort of x extreme, it runs out of kinetic energy, because all of the energy is associated with its potential energy. Where am I writing this? Yeah. So when we run out of kinetic energy, it must be because we're at one of what's referred to as the classical turning points. And the particle, if you check on its ability to exist out here, you never, ever, ever find it in the classical problem, because it's beyond the classical turning point. The particle doesn't have the energy to roll further up this potential energy slope and have a further out value of x, just because of the conservation of energy. Another thing is the particle, in a sort of time sense, spends most of its existence, right, or lifetime, out near the turning points, right? What this means, or the reason why the particle tends to spend most of its time out here, is simply because its kinetic energy is the smallest out there. And if it's the smallest, then it moves the slowest. So it spends a lot of time over here in its lifetime, a lot of time over here in its lifetime, not so much time in the middle, because it passes through so fast with high values of kinetic energy. So in a sense, if you wanted to understand what is the sort of average value of the position in time, it turns out that when you take the average value squared, so it's actually, when you take the value of x squared and you imagine understanding its average value, right? I'm using x squared because presumably it spins equal times with negative x values as it does positive x values. So let's get rid of the positive or negative issue by squaring. So if I understand the average value of the square of the position, it's close to the turning point's position squared. I mean, it'll be just inside, right? It won't be at the turning points, but it's over on the right-hand side. All right, cool. So yeah, this is a fun thing to imagine or try to remember, right? The classical harmonic oscillator. So the quantum harmonic oscillator is solved or explored by the same way that you explore any quantum system that you can describe the energy of. You go straight to Schrodinger's equation. So it starts off like this. We imagine we got this little particle of mass m, and it is subject to a potential that looks like this. This is u of x, but remember you have to multiply by psi of x afterwards, right? And it's equal to some number that represents the energy multiplying the wave function psi again. So here's Schrodinger's equation. And Schrodinger's equation, right, is going to give you wave functions. And the wave functions are likely going to be indexed by some quantum number n, and they're going to be functions of space. And we know how to understand them as being associated with probability density by remembering that you go psi star psi, right? So it's probability density. Okay, so the Schrodinger equation has these solutions. So let's talk about the solutions. So this actually is a hard math problem, and it's the math problem itself, right? Solving this pretty interesting looking differential equation is more appropriate, right? The math problem is more appropriate to do in a more advanced physics class. But these solutions do exist, and lots of people have figured out what the answer is. And it's based on realizing that the wave functions that are going to be indexed by some index n, right? It turns out they're integers. They are proportional to a Gaussian multiplied by something called a Hermit polynomial. So it's a Gaussian shape times a Hermit polynomial is what turns out to be the answer, which is what you could show yourself if you were in a more difficult setting, right? A more technical setting with the topics. But we don't need that. Let's look at a few, right? So if you look in a book, you look on Wikipedia, you just do some web searches, you're going to find that the wave functions, they look like this. The psi sub n, they're functions of x. They're all going to have a different normalization constant. They're going to be multiplied by the Gaussian factor, which looks like e raised to the minus beta squared x squared divided by 2. So that's all up in the exponential, right? So that's the Gaussian aspect. And then we multiply by what are called Hermit polynomials. They're symbolized by capital H. They take the argument x, but it turns out that what's appropriate in this problem is actually not just to study the Hermit polynomials on x. It's actually the Hermit polynomials acting on the argument beta times x. The Hermit polynomials already come with an index n. This thing called beta, which shows up both in the Gaussian envelope and in the Hermit polynomial as a factor on x, this thing beta is related to all of the parameters in our problem, which include the quantumness, the mass and the angular frequency of the classical problem. And it turns out that that beta is the square root of m omega over h bar. All right, so that's what beta is, and beta goes in here multiplying the x, and beta goes up here also multiplying the x. In a sense, beta x is a little bit more fundamental than x by itself, right? So beta x seems to be the interesting variable, not just x. So anyways, let's look at, oh, actually, let me back off that and just say, so the Hermit polynomials, they come with index 0, 1, 2, 3, on and on and on. So there is a 0th index. And it turns out that the 0th index is associated with the lowest energy in the energy series, in the energy spectrum. So the index starts at 0 and can be 1 or 2 or 3, and the 0 is the ground state. N equals to 1 is the first excited state, right? This is different from the infinite potential well, because the ground state wasn't labeled by n equals to 0, it's actually labeled by n equals to 1, right? So the first excited state was n equals to 2 in the infinite potential well. But in this case, notice that the ground state energy is not 0. So this means that if you have a particle, a quantum mechanical system that's a particle subject to a harmonic oscillator potential, that system cannot have energy 0. But the classical system absolutely can have energy 0. All you got to do is take your particle, kill all of the kinetic energy, and place the particle in the middle of the potential at the lowest point. And that'll be 0 plus 0 for its energy, and its energy can be 0. But the quantum mechanics problem, there is no such thing. And this is associated with Heisenberg's uncertainty, right? Heisenberg's uncertainty principle does not let you know x and p at the same time. That is, it does not let you know the location and the kinetic energy at the same time, right? That is, you can't know that they're simultaneously 0, which is the condition you need for the energy to be 0. So it turns out, though, that the ground state n equals to 0, which is, so the energy of the ground state is bigger than 0, and it's 1 over 2 h bar omega. So this is the situation that actually ends up satisfying our Heisenberg uncertainty principle. All right. Okay, cool. So, because this is being recorded, and essentially my screen is being recorded, let me show you what these wave functions look like. I'm referencing the textbook that I'm using for my class, who these videos are for. So let me show you. I'm going to back out of this for a second and go look at here. So there are some pictures of these wave functions. You can see that this is the ground state wave function. If you go and read about the ground state, it's the product of using the Hermit polynomial, which actually is a constant, multiplied by the Gaussian. And the Gaussian times a constant is this orange shape here, low down on the energy scale. because it's the n equals to 0 energy level. It's kind of boring looking, but it sort of resembles a particle being not isolated, but localized by this potential. But you notice that the probability density doesn't go to 0 at the classical turning point. It actually goes to 0 as you go further and further away in an asymptotic sense. That's what the Gaussian does. The Gaussian asymptotes to 0 on the left and asymptotes to 0 on the right. The vertical dashed line is the classical turning point, and the probability extends quite a bit further than that, so that you have probability of discovering the particle in the classically forbidden places. If you look at this function, it's even. That is, it's symmetric, mirror symmetric about x equals to 0. But as soon as you go to n equals to 1, which is an odd number, the wave function becomes odd. The wave function for n, it turns out that this is generically true for the harmonic oscillator. If the quantum number is even, like 0, 2, or 4, your wave function is symmetric about the origin. But if it's odd, then the wave function itself is odd. And that's because that's what happens to the Hermit polynomials. The exponential is always even. You can see the x squared. So the x squared, it kills any minus signs. But the Hermit polynomials, right, the argument is called beta x. So the idea is you put beta x in for y everywhere. If n equals to 1, it's odd. If n equals to 3, it's odd, right? Y cubed is odd, and y to the first power is odd. So the Hermit polynomials are giving us this symmetry of odd or even. Okay, so let me go back to the notes. Yeah. So an interesting thing to point out real quick. So interesting. Is for the quantum harmonic oscillator. The difference between adjacent energy levels is always the same amount. That is, they are evenly spaced. Right? This is true for 1,999, and it's true for 2 and 1. Right? Where we're talking n and n minus 1. So the energy level diagram is evenly spaced. But do you remember that the infinite square well, the energies, right? First of all, it was different because the quantum number index starts at 1. 1 is the ground state, right? But the energies were proportional to n squared. That is, e sub 5 minus e sub 4 is bigger than e sub 4 minus e sub 3, for example, right? So, and that's because 25 minus 16 is bigger than 16 minus 9, right? 16 minus 9 is 7. 25 minus 16 is 9, for example. Yeah, and the energy spacings, or the energies themselves, go up as n squared. And so we're looking at energy differences that are like n squared minus n minus 1 squared, right? Okay. One last interesting comment is the correspondence principle. That is, for n getting really big, our quantum problem gives answers that are really similar to the classical answers, right? So in the limit that the quantum number is really, really, really big, we get these classical answers, or things that more resemble what you expect classically. And the harmonic oscillator, the quantum harmonic oscillator, shows this correspondence principle really nicely, actually. What happens, I love this picture, actually, so let me show it to you. So the picture is, I'm referring to the same textbook. The picture is this. You notice that it's the 12th state. The 12th state is the state with 12 bumps in it. Is that true? Oh no, it's actually, the 0th state has 1 bump. The first state has 2 bumps. Like, I'll show you what I'm talking about. So the 0th state has 1. So 0 has a bump. 1 has 2 bumps. 2 has 3 bumps. When you so there's actually a slight difference between that picture, though, and this picture. This picture is actually of the square. Let's count bumps real quick. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, that matches up. So I expect 13 bumps for n equals to 12, just like I expect 1 bump for n equals to 0. But you notice that this is the square of the wave function, whereas the picture above is not the square of the wave function. It's just plain old the wave function. So the wave function can have negative values and positive values. Okay, but anyways, if you square this, this is more like what you think of when you think of probability. And so that's why it was drawn. So if you go up in a large quantum number, it gives you sort of this picture, right, that shrinks down in the middle and then gets bigger on either side. Now, the reason this is interesting is because the dashed line is actually, let's read what it says. The probability density distribution for finding the quantum harmonic oscillator in its n equals to 12 state. The dashed curve shows the probability density distribution of the classical oscillator with the same energy. Do you remember when I said that when the particle gets out towards its classical turning points, which is where it runs out of kinetic energy and slows down, that's where it tends to spend its lifetime. So that means that if you went to go look for the particle, you're more likely to discover it near the endpoints than at the middle. The classical problem is the dashed line of, if you just randomly look at a classic harmonic oscillator, you're gonna have this probability density. But what's interesting is how similar the quantum problem's answer is to the very same question. And that's the correspondence principle. It doesn't correspond so well when n equals to 1 or 2 or even 3. But if you went and looked at psi sub, say, 1,000 squared, it would just very nearly just like that. The idea is you just don't have really big or like really broad bumps. Every bump is very narrow, is the idea. Okay, so that's it for the harmonic oscillator, or at least my little sort of intro to it.